happy Friday, everyone. Thank you for the section board for inviting me to give a talk here, and thank you for organizing such an event that we can come together to talk about and to learn from each other. So Bob Zeng, again, the newest faculty member in the department. Today I'm going to try to entertain you about a topic that is quite new in ag or in ag systems, which is digital twins, where I specialize using discrete element method to modeling the interaction between your machinery, your crop, and your different biomechanical, biological materials. So today I'll be beginning with an introduction to myself and my research program, and then we'll be looking at an overview of DEM, digital twin, and then I'll be talking about 3 case studies where this technique has been applied in ag production systems in my research program. And then I'll finish with opportunities for collaborations and student involvement in my research program. All right, let's start with a brief introduction. So I am a mechanical engineer turned agriculture engineer, got my PhD in biosystems engineering, and before came into OSU, spent a couple of years in Wisconsin, mainly as a teaching faculty. I taught pretty much any course you can ever imagine in agriculture engineering department, especially in machinery system areas. So right now I'm holding a research teaching split position where my expertise is really on ag machinery and precision agriculture. So my research program, in a nutshell, is really centered on the interaction between soil, machine, and biomaterials for the purpose of designing and producing or innovating advanced machinery. And this ranging anything between tillage to planting to harvesting, post-harvest processing, anything in between, basically. And my research utilizing different methods, including lab tests, mainly for critical machinery components. Throughout the years, my students and I developed different test stands for looking into different interactions of machinery components and biomaterials. Field trials that's basically being used to validating or verifying the performance in the field scale, and they're also engaging with industry partners for the prototype evaluation. Last but not least, my research has been shifted towards heavily focused on modeling, simulation, where I do virtual design and verification, and that will be the focus of today's talk. So digital twin, I'll talk to you what is digital twin and what is multiphysics simulations, and last but not least, DEM, discrete element method or discrete element modeling. Again, I cover everything between lab tests to simulation, but for today's time, we'll be looking mainly in the last one, the digital work. All right, so that's what brings us to the topic of DEM, DT. What is a discrete element method and what is a digital twin? So first, let's try to get a sense of what is digital twin, right? So a digital twin in a nutshell, right, as this diagram illustrates, you have a physical system, and this physical system can be anything. Can be a machine, can be a greenhouse, can be even an entire farm, right? It's just a system. And digital twin is basically utilizing sensor and intelligent system to collect information, data, and to develop a model. So this model is essentially a replica of the physical system. All right? And this can be applied in different scales, different applications, different purposes. And then what's the purpose of doing this? Well, you have a digital copy of the physical system. This essentially allows, as an engineer, right, we can use this to predict the performance, optimize the operations, and then eventually, right, to producing something valuable, feeding back to the physical world. So that's the, in a nutshell, what is the digital twin technique. And then we have many benefits of doing this, right? For the optimization, for decision making, and for training, right? And there's a very low cost, very easy way to get students trained in physical system, right? Think this as somebody playing a video game of farming, right? Except two things. A, whatever you are doing here has a direct impact in the physical world, right? You don't have any tangible impact if you play a video game, right? Here it does. And then B, this system has the potential to optimize itself without any human interaction or with minimal human interaction with the AI and those advanced techniques. The digital model has the capability of optimizing itself based on the data collected from the physical world, right? Which is the difference between play video game versus what we're doing here as a scientific means. All right, so next, what is DEM, discrete element method? It's a computer-based simulation method that we use to simulate and analyze the interaction between individual particles with different boundary conditions with different surfaces. So a couple keywords to describe the DEM is a particle-based simulation, right? Everything you talk about in DEM is a particle or a combo of particles. It's been heavily used to simulate the interaction between machinery and material, right? And in the field of agricultural engineering, we're looking at ag machinery and biomaterials. A very good example to visualize DEM is table tennis. So you have particles, right? That's your balls. You have the boundary. You have the machinery components. That's your walls. And then if you add different contact mechanism or algorithm in place, then you have essentially all the major players in this method. Anyone play table tennis in this room, or have played, or playing? Lots? Very good. Well, so let's say I can use this method to simulate a table tennis match, a game, essentially. And this is all developed with this software, right? So let's say, well, we have two players, right? The one red, that's player one. Black, that's player two. I'm going to simulate a game. Who are you betting? Who's going to win? Well, I have the price of donut, looks like. 2, 1, 1. All right, let's see. I don't know. I did this not long ago. I have different control in place. Let's say who is going to win. Oh, looks like player one win. You can take a donut if you want. Right, so the nice thing about this is I can change in the parameters, the criteria, the mechanism to control who's going to win and by what technique, what method. And I can also plot the trajectory of what happened in this game at the end to show you actually what happened behind the back and forth game. All right, so we'll talk about DTE, talk about DEM. So the real power is if you were to marry or combine those two. That's what we call DEM-based DT. So I'm from a agricultural background, so I'm going to give you a tillage. I'm going to use a tillage as an example to demonstrate the power of DEM and DT. So here on the screen, we have a tillage application. Those are red particles. Those are the soil. Right? We're in Oklahoma, so red dirt. That's the soil we're working with today. And also we're in Oklahoma, we have the wheat, so wheat straw on the surface. And here is a sweep, so that's part of the cultivator machine. Try to prepare the soil for planting, for seeding application. And this is a side-by-side comparison of what's happening in the virtual or digital world versus what's happening in the physical world. And they are being timed in the same time stamp, so you can actually see they match each other pretty closely. So you can say that the model is capable of capturing most, if not all, major soil dynamics behaviors. In other words, they are twins. All right? So this model is able to predict anything you can measure over there, and also is able to give you information that you cannot measure. Right? Those micro behavioral measurements will, to this world, you can never even get into those details, but the model can. Right? So what's the purpose of developing a model like this? Right? Couple applications to demonstrate the kind of the applications. The first one is you can use this to, as engineer, right? We want to know what is the impact of different operational parameters, or as farmer, right? What happens if you run this tillage implement at different speed? So here I believe I have the speed from 4 miles per hour all the way to 14 miles per hour. So 4, 6, 8, etc. from low to high. And you can say what is the impact of the travel speed on your soil dynamics, right? Residue behavior, etc. Right? And they're very different. As you can see over there, the higher speed, there's of course disturbing soil, the further, the more aggressive operation, right? As compared to the low speed is very gentle, very low disturbance field situation. And for engineers, right, this is a very useful tool. It's very handy in terms of in the design process. For example, here we have a disk, same machine. One is at a 0 tilt angle, the other is at a 30-degree tilt angle. What is the effect of soil dynamics in terms of disturbance, forces, etc. Right? How does impact the wear of the disk, the stress distribution of the disk? All those are very easy to simulate with the model being calculated, being validated with the field measurement. Another question we got a lot is by producers, by farmers, right? They have a very different field conditions. That's the beauty of agriculture, right? You have a very diverse, very unpredictable field conditions. In this case, we have a field with wet stubble, right? We want to know that how this machine, this disk, is able to perform in a field like this. So we can also do the simulation to predict what is the soil disturbance and how that impacts the interaction between your waste straw and soil particles. All right, so that's what brings us to the case studies. So hopefully by now you have a basic understanding of what is DEM and DTE, right? Now I'm going to present to you a couple of case studies where we look into using this method in the past of how that can be useful to solve real-world problems or questions. So the first one I'm going to present today is the seed-soil interaction for the purpose of simulating seed germination. So you probably heard this phrase, seed-soil contact, in different situations or different applications, right? And that is one of the most important parameters if you are in the seeding planting world. Many manufacturers, they talk about this machine is really good at maintaining or creating good seed-soil contact, but this is also one of those really understudied or under-researched topic. How do you actually quantify seed-soil contact, and how that's related to your machine performance? So this study, we set a goal to have a model of typical soil conditions with a very simplified version of seed. Over there, we can see what is the process of seed germination in different soil conditions. And here, one of the applications we did was we changing the soil particle size to simulate the soil of more clayish to sandy soil, right? Again, this is a very simplified model. Doesn't have anything, doesn't have all the things you would imagine in your real world. But here is the way that we want to know: does the seed follow the least resistant path, right? We can track the path the seed was taking based on the different soil conditions, different soil types, right? And then we can measure what was the force, moment, and also the distance is traveled from the stem depths to the soil surface. So another application I can say with this type of model is we'll talk about seed orientation in the soil, right? What is the impact of seed orientation, for example, corn, on the germination and the early crop growth, and ultimately on the crop yield, right? And this model is capable of predicting or simulating that, given enough or sufficient data to validate the model accuracy and performance. Another case study I want to present today is the manure application. So basically show you the process, what is the typical process of developing such a DEM and DT model. So start from, as an engineer, right, start from a very basic sketch, and then to a CAD model, right, that's the first prototype we proposed. And then the magic or the trick here is between the CAD model to the actual prototyping, we put in the DEM, DT model, so that, of course, it's able to identify the problems, to predict the performance, to optimize the system before you put any dollar into prototyping or manufacturing such a system. So we have the discrete element method being used to predict what is the soil dynamics. We have the FEA, which is a very popular tools or conventional method of validating the strengths and of the machine component. And then through all those, we were able to produce the first prototype of the idea with a satisfactory field of performance. And then the goal is to be able to pitch the idea to major manufacturers to offer to the commercial farms, to the farming industry, and we have a pending patent on this design and this system. Another application where we look at forage separation or forage fractionation. So basically the idea is we have a very diverse material, forage, right? That could be corn silage, could be alfalfa headage. It's diverse. You have anything from the stem to the kernels, to the leaves, which one is very energy intensive, the other is more heavy on fibers. So we want to develop a system that can separate those two different streams of materials to be able to produce a high quality feeding material. So that's the CAD model or the idea, and then we have a very preliminary or benchtop physical model, so we can use that to collect some data to feed into the digital model. So that's a comparison of what's happening in the real world versus the digital model. And then we can collect a bunch of information with this model, right, in terms of what is the distribution of the material, the quantity, the composition of the materials. And that was the first prototype we developed. We can use that to collect more data and feed back into the model, and that's a cycle a process for the prototype. All right, so that's what happened in the past, right? What has been done as far as what we are able to use this DEM, DT techniques to solve real-world problems. Now let's looking ahead. What are some of the opportunities for collaboration and involvement? So before I get into the my vision of ag machinery or production. Let's get your opinion, right? So by show of hands, what do you think of American and Oklahoma in terms of agriculture? Do you think that we are in a good position in terms of ag production, in terms of agricultural impact to the world? Hopefully you think it's pretty strong, right? Now let's change the question. What do you think of American or Oklahoma in terms of manufacturing, producing machines, producing devices, allow others to be able to farm, to produce feed, produce food or fuel and fiber? Well, so hopefully you agree with me, right? American is really a powerhouse in terms of agricultural production, right? We are top in the world in terms of producing food, fiber, and fuel, right? And Oklahoma is a really a strong contributor, especially in commodity in wheat, beef, poultry, and especially crops. Right, that's the picture of agriculture, right? We are doing pretty good. Now, if you look at manufacturing, right, what's happening there? That's the data from 2020, right, 6 years ago. The data show that in terms of the value added as a percentage of GDP, America is in the middle, right, or pretty low in the G7 nations. Japan is almost double us in terms of the percentage to the GDP. So there's a gap, right? And I see that as opportunity as well, right? So we have a very strong agricultural sector, has a very moderate manufacturing sector. So my research program is really positioned to bring that, bridge that gap. And that's where I am here. And I think, or I believe, Oklahoma is positioned in a way to leading that effort, knowing that agriculture and manufacturing are the two most dominant industry in this state. So we're in a good position. We just need to bring resources, bring effort together to moving in that direction. All right, so that's my vision. Of course, I cannot do this alone. I am a mechanical engineer. I'm an agriculture engineer specialized in machinery system. So I know how to design machine, I know how to test, how to simulate, but I don't know much other than those areas. So I often collaborate with to working together to be able to produce something that farmer can use, can be put into a real world application. And of course, right, students is a major part of this of those research, of this effort. So I see myself as an educator before researcher. So I want to work with students. So there's a barcode. I'm still recruiting a couple of grad students and a postdoc to help me develop in this effort. So I appreciate if you can spread the word and then help me to recruit students that would be able to help me working together to moving in that direction or division. All right, 23 minutes. Thank you for your attention.
Dr. Zeng, about how long was one of these model setups, how long was the simulation and so forth take before the actual application?
So the question was, how long does it take for the model to be able to develop to the stage that you can actually put that into application? So it depends. That's the question for a couple of reasons. One, depends on what scale you're talking about. For example, if you're talking about the scale, you can use the model to produce information for controlled environment for lab tests. That will be pretty short or pretty fast. But if you're talking about be able to develop a model that can be used for field scale application, and that can take months or years. That's one thing. The other thing is, to what extent is your definition of application, right? Because for any model, you have a different extent or different level of accuracy, right? I talk about almost there, or I talk about 95% accuracy. So that's also another thing, how accurate you want the model to be. So the manual application project, we probably spent a year and a half, so we can use the model fully validated to be able to answer pretty much any question you might have in your field application. So just give you an example how long it took for that model.
Question for you. I saw the interactions with soil and implements in there. Can you do a digital twin on looking at the impacts of conservation tillage or no tillage and kind of like soil health type related parameters?
Sure, that was my PhD study. So we look at conservation tillage with a very high crop residue coverage versus a more intensive tillage system. We did not get into the soil health aspect yet because well, still mainly focus on the mechanical aspect.
Yeah.
But it's
I can see that being very attractive.
Very possible collaborating with a soil scientist or somebody who has the background. How can we relate those mechanical behavior with soil health aspect?
Very good. Thank you very much.
Well,
One more question. Yeah.
So about digital twin, so I understand the concept that you try to model the physics with some computer model, but another important component is the sensors that get real-time information. So in those case studies that you were explaining, do you have some sensors in somewhere that provide real-time information for you? Digital twin.
Yes, for the sensor, there are two different, in my view, there are two different categories. One is, well, anything you measure, that's a sensing activity, right? So for the model we developed so far, it is still early stage, so we do not have real-time sensor or real-time sensing capability yet, just to show you the capability of this technique. So the near future term is to integrate real-time sensing components into this, and then also that would allow the model to predict or to provide real-time information back to the physical system. The one I talked about today, those case studies, we mainly use either manual or not real-time sensing technique to be able to develop some conceptual model at this stage. I think
Okay, if we use your computer for the next talk too.
Sure.
Okay. You have your presentation. Yeah. You want to be able to put that into my computer? you won't let it. So. All right. Thank you, sir.